October 21st, 2018. Just before 11 at night, universal time. A maintenance crew swaps out a failing piece of 100 gigabit optical gear. Routine work. But for the next 43 seconds, GitHub's East Coast data center cannot hear the rest of GitHub. Watch the link. It's cut. Both halves are still alive. Users are still pushing code to both sides. Nothing crashed. And that is exactly the problem. Those 43 seconds are about to cost GitHub more than 24 hours. One day, the network splits in two. This was that day. And behind it sits a theorem that decides what happens next. It's why your banking app sometimes freezes on a spinner, while your feed loads instantly and lies to you. Why a cash machine will hand you money it isn't sure you have. And why, when the wire snapped, GitHub faced a choice that no amount of clever code can dodge. Not slow code. No code. It's math. Start with why the wire matters at all. One machine is one power cord, one disk, one building that can catch fire, so real systems keep copies. The same data on machines in different racks, different cities, different coasts. GitHub ran its primary databases on the East Coast, with replicas standing by out west. Copies are how you survive, but the moment there are two copies of anything, you've created a brand new question. Do they agree? And keeping copies in agreement means talking. Constantly. Here's the usual arrangement. One copy is the leader. Every write goes to it. The followers tail the leader's changelog and replay every write in order, like a stenographer copying a transcript. Now, one decision changes everything. Does the leader wait for the followers to confirm each write before telling the user, done? Waiting is safe, but slow. Painfully slow when a follower is a whole continent away. Or does the leader answer immediately and let the followers catch up? That's fast, and almost everyone picks fast. But fast means the followers are always a heartbeat behind, and you have felt this. You post a comment, the page refreshes, and your comment is gone. You refresh again, and it's back. Here's what happened. Your write went to the leader, but your very next read landed on a follower that hadn't replayed it yet. You asked a machine that genuinely didn't know yet. That's not a crash. That's not even a failure. That's just replication lag on a normal Tuesday. It's a group chat where one friend's phone is in airplane mode. The moment the phone reconnects, 40 messages flood in order, and now everyone's chat shows the same history. Late, but converging on the same truth. Engineers call this eventual consistency. And notice how gentle that failure is, because the follower always catches up. The wire always comes back. So ask the darker question, what if it doesn't? Cut it. Not slow. Cut. Two halves of the cluster, and each half is perfectly healthy. Users on the left can reach the left side. Users on the right can reach the right side. The two sides just can't see each other. Now a write arrives on the left, and a write arrives on the right. Every machine in this picture is working correctly, and yet the system is standing on the edge of the worst decision in distributed computing. What should each side do? Now the key step. The left side would love to check with the right before answering, so it sends a message. And here's nothing. Is the right side dead? Or just slow? Here's the brutal fact. Over a real network, there is no way to tell the difference. No timeout is proof. Silence for 1 second, silence for 10. A dead server and a slow wire look exactly, perfectly identical from the other side, which leaves a node holding a write with exactly two moves. Move 1, answer now, without cross-checking. The user is happy, the system stayed available, but the two sides can now drift apart. Two versions of the truth. Move 2, wait for a confirmation that may never come. The copies stay consistent, but the user gets no answer. Maybe forever. Every protocol ever invented, no matter how clever, ends in one of those two moves. That is not an engineering limitation. That is the entire proof. Two friends selling tickets for the same concert. At 2 doors, 1 seat left, and their phones just died. Option 1, a seller stops selling until the phones come back. Nobody gets double booked, and customers walk away from a working door. Option 2, both keep selling. Everyone gets an answer, and 2 people may buy 1 seat. Sit with it as long as you like. You will not find a third option. Nothing fixes this, except the phones coming back. In 2000, Eric Brewer stood up at a conference and conjectured exactly that. Through a network split, you don't keep both consistency and availability. 2 years later, Gilbert and Lynch turned the conjecture into a proof. The CAP theorem. And the word theorem is doing real work in that sentence. This is not a best practice that better engineers escape. It sits in the same drawer as the laws of physics. You don't fix it, you plan around it. Now you may have heard the pop version. Consistency, availability, partition tolerance. Pick 2 of 3. That framing is wrong, and Brewer himself wrote in 2012 that it was always misleading. Here's why. Partitions are not a menu item. You don't get to not pick them. Cables get cut, switches die, maintenance goes sideways. Partitions are the weather. The honest statement is smaller and sharper. When a partition happens, choose consistency or availability. When the network is healthy, you get both. The theorem only bites while the wire is down. One more precision pass, because both words are stricter than they sound. Consistency here means the whole fleet behaves like one machine. Once a write completes, every later read, anywhere, sees it. The fancy name is linearizability. It is not the consistency from database transactions, the acid kind. Same letter, different universe. And availability means every request to a working node gets a real answer, not an error. It does not mean 5 nines of uptime. Keep those strict meanings, and every confusing blog post about this theorem untangles itself. And once you see it everywhere. Your banking app freezes on a spinner and says, "Try again later." It would rather be silent than wrong. It leaned consistent. Your social feed loads instantly, every time, and quietly shows you a like count that's already stale. It would rather be wrong than silent. It leaned available. Same theorem, opposite bets. So how do real systems place that bet on purpose? 2 famous designs, and each one runs half the internet. Design 1. Refuse to guess with a majority vote. Take 5 copies, and require that a leader hold votes for more than half. Now cut the cluster 3 against 2. The 3 can still form a majority, so they elect a leader and keep serving. The 2 can't, so they refuse rights on purpose. It's the ticket sellers again. With 3 sellers, the pair who can still talk keep selling, and the loner stops. This is Zookeeper, and the coordination store at the heart of Kubernetes, and why those clusters come in odd sizes, and the users stuck on the minority side get errors. That is the sacrifice, working as designed. Design 2. Never refuse and clean up later. In 2007, Amazon published Dynamo, the design behind a shopping cart, with one commandment: always writeable. Rejecting an add to cart is a lost sale, so during a partition, every side keeps accepting writes. When the wire heals, the diverged carts are merged by union. Anything added on either side survives. The catch: a delete can lose to an older copy, so an item you removed can crawl back into your cart. Amazon chose that bug. Losing an add costs money. A resurrected delete just annoys you. Now the twist. You'd bet your bank sits all the way at the consistent end. But Brewer's own favorite counterexample is the cash machine. During a network outage, a cash machine can keep dispensing. It just caps you at something like $200 until it can see the ledger again. The bank bounds how wrong the answer can get, then fixes the books later, with an overdraft fee if it must. In Brewer's words, higher availability means higher revenue. The bank chose available with a blast radius and a bill. So is a database a consistent type or an available type? The honest answer is, per query. Cassandra leans available by default, but consistency there is a dial you set on every single read and write. Confirm on one replica, fast and forgiving. Demand a quorum, or every copy, slower, stricter. Set the dials so your reads and writes are guaranteed to overlap on at least one replica, and you're back to strong guarantees. One database, both ends of the spectrum. The labels describe decisions, not species. And most real systems, strictly scored, are neither. One last upgrade, because CAP only speaks to the disaster case. Replication charges rent even on sunny days. Wait for your replicas, and you're slow but right. Don't wait, and you're fast but a heartbeat behind. That's the extension on screen. If partitioned, availability versus consistency. Else, latency versus consistency. Your vanishing comment from earlier was the else branch. You weren't in a disaster. You were standing in the gap that being fast leaves open. And a gap one October night is exactly where GitHub fell. So rewind to October 21st and read it like an engineer. The maintenance work severs east from west for 43 seconds. East Coast primaries, cut off, keep accepting writes. On one busy cluster, 954 writes land in that window and never replicate west, 43 seconds. Under 1,000 rows. On the scale of GitHub, that is a rounding error. Hold that thought, because that rounding error is about to eat an entire day. GitHub's failover system, a tool called Orchestrator, runs on a majority vote of its own. The Orchestrator nodes that could still see each other, West Coast plus Cloud, formed a quorum. concluded the East was gone, and promoted West Coast databases to be the new primaries. In the moment, the system chose availability. Keep serving. So for roughly the next half hour, fresh writes piled up out west. Writes the East Coast copies had never seen. 2 primaries. 2 histories. A split brain. When the wire came back, GitHub faced the Theorem's bill. 2 diverged histories for the same databases. Their own postmortem put it in one line. We prioritize data integrity over site usability and time to recovery. Read it plainly. Your code, your issues, your pull requests, they refused to guess. They paused webhooks, paused site builds, and settled in for the slow, honest fix. Because when 2 histories disagree, there are 3 ways out. Last write wins. Keep the newest timestamp and silently discard the rest. Simple, and it quietly throws data away. Semantic merge. Like Dynamo's cart union, when the data has a shape you can merge. Or, when the data is too precious to guess about, the human scale rebuild. Restore from backup and replay history until every copy reconverges. Shopping carts can merge. Your repositories cannot. GitHub took door 3. That decision is the whole timeline. Restoring multiple terabytes from backup took hours. Reconverging replicas across 2 coasts took longer. In total, 24 hours and 11 minutes of degraded service. And when the pipes reopened, the backlog surged through. Over 5 million webhook deliveries and roughly 80,000 paused site builds, replayed in order. No guessing. No silent overwrites. That was the entire point, and it was paid for, in hours. Do the division. 43 seconds of cause. 24 hours of consequence. That's a blow-up factor of about 2,000. And remember the trigger. Not a hurricane. Not a hack. Scheduled maintenance on a failing part. Surveys of real data centers keep finding the same thing. Partitions are not exotic. Rare, maybe. But rare, multiplied by unhandled, equals catastrophic. The theorem does not care how good your uptime was last quarter. So close the loops. Partitions are weather, not a menu. You never got to pick 2 of 3. When the network splits, there are exactly 2 moves. Refuse and stay right, or answer and risk drift. A majority vote is how you refuse safely. That's Zookeeper, and the brain of Kubernetes. Merge and compensate is how you answer gracefully. That's Dynamo's cart, and the cache machine's $200 cap. On healthy days, you get both, minus a latency tax. And no system is a species. Every one of them is a stack of these choices. One thread is still hanging. GitHub's fix leaned on restoring from backup, terabytes of it, trusted completely. But hang on, databases lose power mid-write all the time. Half a row written, then darkness. Why isn't the file just corrupted? There's a beautiful trick underneath, called the write-ahead log. That's a story of its own. Back to the frozen picture. The cut link. A write, hovering on each side. 43 seconds, and GitHub spent a day paying for them, on purpose, because refusing to guess was the design. That's the real lesson of the theorem. You can't cheat it. You choose, before the failure, what you're willing to sacrifice during it. Or the network. Some quiet Tuesday night will choose for you.